Got it. And hello, YouTube. Welcome. Record to the cloud. You got it. Like this. All right. It's great to see everyone again. Like that. Yeah. All right, we made it. We made it to the end of the semester. Students, how you doing? Yeah, like 3 thumbs up. But they were from 2 people. Everyone else is suffering a lot. Okay. Well, you made it. It is close to the end. And we have our final speaker of the semester. So again, an alumni from the Center for Wetlands. Today, we're lucky enough to have Dr. Charles Lane. So Chuck, welcome back to this room. Charles was telling me that he had his qualifying exam in this room and was up against the board. You know, we're deriving Michaelis Menten equation, which most of you are familiar with, and got just right to the end. So despite that, he came back. I really appreciate it. So Dr. Charles Lane is a senior research systems ecologist with US EPA's Office of Research and Development in the Ecosystem Processes Division. I didn't know you have an undergraduate in economics, or does that change how you view all of this biophysical research in some way? No, just perspective. Okay, nice perspective. Then, of course, he got his MS and his PhD here in systems ecology, and his advisor was Dr. Brown, both of those. Joined the EPA in 2003, so coming up this 20-year anniversary there, and focuses a lot on wetland hydrology, particularly these things we call non-floodplain wetlands. I won't give away any of the story there, but they're really important from a regulatory perspective and, of course, from a geological perspective. And he's had a really cool career in as a federal research scientist, doing the science that supports the protection of wetlands and able to have some flexibility in choosing what he wants to look at. And so I think we'll hear a lot of those stories today. Yeah. All right. Thanks, Chuck. The floor is yours.
Thank you. Thank you, David. And thank everybody for taking the time here. It's great to be back at the Center for Wetlands. And again, that table is here and this chalkboard and Mark. I just changed. But it is great. I really appreciate the opportunity to come to present to the Center for Wetlands. And I'll be presenting perhaps myself on behalf of myself and Heather Gold and Jay Christensen. We're a team. We've been working together for about a decade now, focusing on non-floodplain wetlands and what they do, where they are, how they function, and why we should care. And so with that, this is the roadmap of where we're going. Let's see. Okay. Right. So we have we'll talk a little bit about the resource extent. It's going to be kind of like a journey of where we've been going over the past couple of years with our research in non-floodplain wetlands. We'll talk about what the resource is in the CONUS, contiguous US, and then globally. Some of the research on why we care, some of the outputs of our research team in hydrology, biogeochemical aspects of non-floodplain wetlands, and a little bit on conclusion, challenges for you all, and then time for questions towards the end. And disclaimer, of course. So what are non-floodplain wetlands? So these are wetlands that are off the geomorphic floodplain. And I say geomorphic in parentheses because we use a distance as a proxy in some cases, or we get into actually delineating the geomorphic floodplain itself. There are wetlands that are completely surrounded by uplands, and also known as geographically isolated wetlands. That was the nomenclature we used up until around 2015 or so, and then we kind of morphed away from that into the non-floodplain wetlands terminology. And a couple of pictures showing the California vernal pools when they're full and then dry. These systems have varied hydrology. Sometimes they're inundated, sometimes they're completely dry. Sometimes they're very small, like some of these woodland seasonal ponds up in New England. Sometimes they're much larger, like some of those playas down in the western, northwestern Pennsylvania, Texas, and other areas. Prairie popple is probably the most iconic of the non-floodplain wetlands, an area that spans Canada and the United States. And of course, down in Florida, we've got a lot of them, like these flatwoods ponds, and then cypress stones. And we've got a picture from the inside of one of the cypress stones. About 20 years ago, Ralph Tyner went through and identified around 29 different types of wetlands, which could potentially be non-floodplain or geographically isolated wetlands. And there's a whole list here from that wetlands special issue in 2003. We're not going to show pictures of all of them, but they're out there and they're quite wet and looking. A few years ago, Ellen D'Amico and I worked together to essentially create the first map of potential non-floodplain wetlands across the CONUS. And this is using the National Hydrography data set and the NWI. And you can see that areas of the Prairie Pajaro region are well represented, the Playa wetlands down in Texas, Texas coastal ponds, and of course, all of Florida. It's pretty much replete with wetlands, non-floodplain wetlands. Most of them are to the east of the Rockies and the aridity gradient that exists therein, but there are areas in the western part of the United States where you do have non-floodplain wetlands or wetlands that are out of the British Channel area. And so it is a CONUS resource, a resource available throughout the United States. We redid this a couple of years later, looking at using a Google Earth Engine approach, same kind of result. This is a different map showing watersheds below it. And then in this paper, these are just kind of setting the stage of what the resource is out there. You'll see the grouping here is from 29 to 99%, but this shows the different HUCs. I think these are HUC 10s, I want to say. The watersheds and the abundance of non-floodplain wetlands within. So the darker green have up to 99% of the wetlands in that basin are non-floodplain wetland systems. Which up until recently had varying degrees of protection afforded to them. So the net of the story of where non-floodplain wetlands are in the United States would be, we have roughly 8.4 million of them. They're about something around 16 to 22%, depends upon some of your particulars of how you analyze their location in space. They're definitely small. So the median area is 0.2 hectares, which is relatively tiny. And they're challenging to map because they're seasonally or temporarily flooded quite often. And I recognize now that people that are online can't see the pointer. So if I need to do anything,
you can either use the mouse or you can use the stick and point to the screen if you want. Yeah.
Right.
Yeah.
So that's kind of setting the stage within the United States. Now let's kind of dial it back a little bit and look at the globe, right? Let's dial it back, look at the globe. Let's kind of go up a level and look at the globe. So generally speaking, I'm sure you guys have all seen this one before. This Tom Dahl from 1990 shows that in the United States anyway, we've got roughly 50% of the wetlands have been lost, right? And we've all seen this map beforehand. Some states have quite a bit. Iowa, for instance, have quite a bit of wetlands lost. Florida and like South Carolina have smaller amounts of wetlands that have been lost. Again, this is since European arrival in the United States, 50% of the wetlands have been lost. That was from 1990. So I'm kind of hoping that we'll get a new analysis sometime soon about it. What is it about the wetlands out there? What does that look like? Here's an example from Iowa. On the left-hand side, you can see what it could have looked like back in the day, as we say, using LiDAR to identify depressions and soil to look at hydric soils. That's what it could have looked like. You can see some of the areas where some of the glaciers, the glacial extent, and different rains and such that have developed down here. And this is what it kind of looks like these days. Not a lot of wetlands out there. Another one you've probably seen beforehand. We have, I believe, there's going to be a new status and trends document coming out shortly, but this shows as of 2009, our annual loss is something like 14,000 acres. I'll say that the past 15 years or so probably hasn't been too good for wetlands in terms of the protection and conservation across the country. So we will see what it looks like now, but we're still losing about it. And what are we losing? So this is a paper that Irina Creed and others looked at, where they looked at the extent of wetlands that are still in the landscape, using a power law function to identify where you would expect to see wetlands and the abundance of them. And what I want you to see and kind of take with me here is how this curve continues to kind of grade downwards. So this would be the initial loss as the Prairie Pajaro region where they did the study was starting to be agriculturally utilized. And then by 62, this curve drops further, then 93 and 2011. And you can see that where this line would likely hit the y-axis continues to kind of go south. So the larger wetlands, more of them stay on the landscape. The smaller ones are starting to be preferentially lost. Irina Creed and I and others continue this kind of focus on vulnerable waters, as we call the non-floodplain wetlands and headwater streams, looking at their abundance across the globe, using a couple of different types of analyses. But the takeaway here is that the losses in red by continent, in general, have been bad and been pretty that depending on your perspective, but there's been a lot of wetland loss in the past 120 years or so. ATN Chouinard et al. Recently released a paper where they did a similar analysis. The reason I like this paper is because it shows this graph down here. There's a lot of information on here. So this one right here I thought was pretty interesting because it showed what happened to the wetlands, why were they lost, what was the rationale, the reason for them, and the transition was that as they had found, it's mostly been to cropland or rice or a different type of crop, I guess, out in the landscape. And again, it kind of supports that the United States and other parts of Europe, Southeast Asia, have lost a lot of their wetland resources. But we don't know about the non-floodplain wetlands, geographically isolated wetlands across the globe. And so one of the things that we identified in that paper I showed you was that there isn't a map of such, or even a data set. There wasn't a data set. And so my colleagues and I recently released it. We found a data set, we developed a data set that we then released in Earth System Science Data, papers mapping global non-floodplain wetlands. And in order to map the non-floodplain wetlands, we had to figure out where the floodplain was and then where the wetlands were. It sounds kind of simple, but it's kind of challenging in the end. To develop a floodplain, we use a really neat algorithm that Fernando Nardi and others have released called GFplane, and they released GFplane 250, which use the SRTM, a shuttle radar topography mission data to then develop several input data layers: drainage network, drainage area, flow direction, elevation, and there's a relationship between the contributing area and the depth in each one of these grid cells. And then they developed their floodplain with relatively high accuracy. That was the area where the amount of water, the depth of the flow in the grid was greater than the elevation of said grid. So we used their approach, but we used a 90-meter data set that was released, the Merit Hydro data. And in these images are just contrasting the 250 and the 90-meter resolution. You can see in yellow, compared to the 90-meter, that there's a wider extent of the floodplain, the southern portion of, this is South Carolina, I think, southern portion of the basin. And then zooming into the more distal parts of the network, you can see how our, this is Mississippi, sorry, the Missouri River now, coming down through here. And you can see how the 250 meter stops here, but the 90 meter goes much further up into the network. So we thought that looked pretty good, but how does it look versus how does it compare to other available data sets? Sean Woznicki and others in 2019, I think, released a random forest based map of floodplains across the CONUS. They used 30 meters in their data set, and their data set was based upon the FEMA, the Federal Emergency Management Agency flood insurance rate maps, FERM data, which are pretty, they're pretty intensely developed data sets. It takes a lot of effort to make a FERM map. And so we used that as our baseline, and we found that our floodplains are actually pretty good relative to their CONUS-wide available maps of 30 meters. And this just shows where the 21 basins that we explored were across the climatological gradient. So we had lots of different basins across lots of the country. One thing was that they used a 5 kilometer squared contributing area, and we used a 20 kilometer squared contributing area. But nonetheless, we still had 80% accuracy. So we were pretty content with that. And here's another example of it. I think it's the same basin where you can see the Woznicki data is in this magenta, and where we and the Woznicki data set overlapped was in orange, and then our further extent, slightly further extent, is in blue. So we're pretty happy with our flood maps. There's the takeaway. Wetlands are they're tricky, right? And so the reason I have this map up here is this is our data that we used by Tucci et al. And they publish in Earth System Science Data as well, where they had 2 different types of wetlands that they used to develop their global map of wetlands in general. And this is released in 2019, I think. The regular flooded wetlands are based upon satellite imagery. And then they also incorporated a groundwater set, a groundwater supported or driven wetlands from a data set that was released by, I think, Fan et al. From 2013 in Science. And so water that was within 20 centimeters or so of the Earth's surface is the groundwater supported wetlands. And then the regularly flooded wetlands are the ones that are inundated and able to be discerned by satellites. There's a lot of information here, but the takeaway here is what Tucci et al. Did was they use an all or nothing approach. And so with their 500-meter cells, you had to have at least half of that cell had to be wetlands in order to be considered a wetland cell. So they took the PECL data set, the global surface water, CCI, the GEMS, E15, and their own data set, and merged it all together and said, if more than 50% of this 500-meter cell is wetlands, we'll call it a wetland. Now, we found that to be good as the first start, and they had a pretty good resolution, pretty good accuracy with other global data sets that were in that same resolution of 500 meters. But we wanted to get the smaller wetlands. You recall that most of the ones that we're looking at, the non-floodplain wetlands, are smaller, right? So our map, relative to the Tucci et al. Data set, we had a 33% increase in precision, 20% increase in critical success. I mean, all the metrics that we use compared to the national land cover data set for non-floodplain wetlands, we found that all of our metrics were a pretty substantial increase over their data set. You can see here in magenta are the ones that we got correctly. The green were essentially commission errors where we estimated more than was existing in the benchmark data of the NLCD. And one thing I want to point out is that using NLCD, a 30-meter data set to challenge your data set with, or the data set that we published was, I mean, we kind of set ourselves up to fail because that's a really high resolution data set, and they use a lot of information in there, including NWI and other data sources to delineate their wetland resources. So we kind of expected that we wouldn't be as accurate as we liked. Nonetheless, we're pretty happy with the overall accuracy of our map product, and it's certainly only the first flush in terms of where we're going for a global non-floodplain wetland data set. But we were able to find that 16 million square kilometers of the globe is covered in non-floodplain wetlands. You see high densities in Siberian Russia and in the northern parts of Canada, and then also in the Amazonian basin. So we're pretty happy with the fact that this data is out there for people to start using, because that's one of the challenges that we've had is that people don't know where the wetlands are, and so they don't incorporate them into their data sets. So now, why are non-floodplain wetlands important? So now we know where they are as we go down this journey. And what time will you finish?
12:35, but I'll give you like a 10 minutes and.
Okay, good. Thank you. All right. So most of the time I spent my work looking at the hydrology or the biogeochemistry of the system. But I did want to throw up a couple slides of talking about some of the connectivity and effects for wildlife habitat. So Craig Allen, you guys might know, used to be a researcher, got his PhD in wildlife ecology, then went on to still a researcher, but he got his PhD in wildlife ecology at Florida and went on to work at the co-op in, I think he's still in Nebraska. And one of his students was looking at the rainwater basin in Nebraska and showing how historically the distance between two different points, two different wetlands on the landscape was around 480 meters. But because of development and wetland loss, it's now over 1,000 meters. And that has a substantial impact upon a lot of the annual species that use this landscape, this wet landscape, for breeding and habitat purposes. Similarly, Daniel Uden and others and Craig looked at what would happen with the flyway in, again, Nebraska. There's several different flyways that we have for migratory species, and Nebraska and the sandhills in Nebraska are very important. Currently, they had a model that predicted the inundation in these wetland landscapes, and with different types of change into the future, most of the wetlands that they're predicting that existed would no longer be inundated, which would have this pretty substantial impact upon the migratory birds that are using the Midwestern, the Central Flyway. But that's not really where we've been spending our time. We've mostly been spending our time in the hydrology world, the world of hydrology, and in nutrients over the past couple of years. And so I'm going to be spending the next several slides actually talking about some of the research, some of our findings that we found in working with our postdocs as well. And so a lot of the work is being led by our postdocs, and I'll try and identify their work as I can. I just wanted to throw this up here. I found this to be interesting because you've seen a lot of maps that show where the landscapes are drained across the country. We talk about it a lot, but it's really hard to identify where the actual tiles are out there and where the landscapes are drained. And I found this map from Purdue, which showed where the agricultural interests, for the most part, have drained the landscape to manage the water on the croplands. And so this, I just thought it was interesting to contrast between the abundance of non-floodplain wetlands and the drained landscape, if you will. So the water has been drained, and what does that mean? What does that mean for hydrology? So Nate Jones, who was working with Danny McLaughlin and others in the Chesapeake Bay region, looked at the landscape, the wet landscape, and what happens when you've got lots of drained lands and you decide to hold the water back for flood potential, flood mitigation, and also for nutrient dynamics. And so they found that just the simple function of damming or blocking these ditches that are draining the landscape could increase the water storage potential on the landscape by 80%. And so we're like, oh, okay, that's kind of interesting. So what if we were to start looking at the abundance of these depressions on the landscape and look to see how they affect the movement of water at a large spatial extent? So this is the Upper Mississippi River Basin. And this research was done by Adnan Rajib, who was a postdoc with Heather and Jay and I for a couple of years, and now is an assistant professor at the University of Texas. And so this map shows the depressions in the landscape, which we're calling the non-floodplain wetlands, and their potential storage volume, right? How much water could they hold? I developed a high-resolution SWAP model, and this is kind of the nuts and bolts of it all. But the takeaway is we got this spatially resolved SWAP model where we looked at the storage of water on the landscape in these depressions. And the findings are pretty interesting in that when you don't incorporate depressions and non-floodplain wetlands in the landscape, you have this conventional model. And most of the models don't even consider non-floodplain wetlands, where you have somewhere between 100 and 900 millimeters per year of water yield. When you do incorporate the depressions, the non-floodplain wetlands in the landscape, you have a much different reduction in the water yield in each one of these sub-basins we looked at. Now, we tested this, and of the entirety of the basin, this is about 500,000 square kilometers, 70% of that had a significant different water yield between the two different models. So you incorporate non-floodplain wetlands and their storage potential, and the water stays in the landscape. And what does that mean in kind of reality? And this is reality in quotes, because this is a modeling exercise. So this in black is the USGS gauge, and we analyzed something around like 24 gauges or so in the area, and about 2/3 of them had a different signature when the depression integrated model was used. So, for instance, this is the blue line is without, and then the red line is with the depression integrated model. So you have an actual substantially different response, hydrologic response in the SWAP model when you use the depressions and you incorporate them into your model. We similarly, and I apologize, I flipped the colors in this one. Heather Golden led a paper where we were looking at non-floodplain wetlands and again, trying to get folks to incorporate these systems into their modeling exercises and efforts. And this is in the pipe stem, which is about 1,800 square kilometers in northern North Dakota. When the non-floodplain wetlands were incorporated into the model, the 50-year flood was barely reached, if at all, and the 100-year flood would not be reached. And so versus when they're not incorporated into the model. So the gist would be that if you don't incorporate these wetlands into your model, you're probably going to have erroneous outputs, at least in some places where you have on a high abundance of non-floodplain wetlands. So if wetlands are able to store water in the landscape, what does that mean for the nitrogen dynamics on the landscape? You know inherently that wetlands are good places for nitrogen to be removed by various microbes. So we started looking at the ability of non-floodplain wetlands to remove nitrate from the landscape. This is done by Samson Mengistu, who's now with Bayer Corporation as a postdoc. We developed a linear model that related the abundance of nitrate in the streams to different landscape variables. And then we incorporated additional landscape variables and tested how that model functioned. And we found that when you incorporate different flow path, FP is flow path, so flow path variables from the wetlands to the stream system, that areas in green are significant, that you would have a significantly different response in the stream. So for instance, we have watershed wetland drainage. The more watershed wetland drainage you have, more water that goes into the wetlands, then the lower amount of nitrate you have in the stream systems. So we're like, all right, well, that kind of makes sense. I mean, we thought that would be the expectation, and we're pretty content with the way that models turned out. But let's go look at it now with like a process-based model. And this is work that Gray Evanston, who's now with Linker Corporation in Columbus. He was postdoc with both Daniel McLaughlin and Heather J. and I for a while. So we're looking again at the upper Mississippi River Basin, and you remember that goes from up in Minnesota all the way down to what, central Missouri or so. And I wanted to kind of highlight the tiled landscape. And so these are some of the inputs and the outputs. We were curious on the what extent. Well, the question is, to what extent will a non-floodplain wetland restoration affect nitrate loads in the basin? We looked at the sub-basin level, so each one of these little sub-basins, we had 279 of them, and then we looked at the basin outlet, which is down here somewhere. And you can see that a lot of the area with potentially restorable wetlands are in this darker blue, and there are also areas where there's a lot of agricultural activity going on, and a lot of nitrogen is being released. So we found that in most places, when subbasins are have wetlands restored on the landscape, for the most part, not only will the subbasin remove the nitrate, you also have a nitrate reduction at the basin outlet down here. But there's some basins where that didn't work, where there really wasn't an impact upon with the restoration. Those are mostly in the upper part of the network. And there are others that were a little bit lower in the network. But part of the question that we were looking at as well, this is an interesting finding for the impacts of wetland restoration in the basin, but why is it that those ones that are so far away are not having that much of an effect? And I'll get to that in a sec, because we have another postdoc who's working on that sort of question. Well, one of the things that we found with this study was that when you restore about 8,000 square kilometers of wetlands in this basin, which is an increase of about 33% of what's out there currently, you would have a 12% load reduction. And so that's a 12% load reduction, which is a lot less than what others have been finding in the upper Mississippi River Basin. And we found that that was mostly, we're hypothesizing, it's mostly because of the tiling that's out there. And so 2 out of 3 units of nitrogen that make it into the basin outlet go through tiles. And so we're kind of, all right, well, if the nitrogen is not being seen by the wetlands, they're not going to do anything to it. So Gray took a slightly different modeling approach here, where he ran several thousand SWAT model iterations and looked at the range in nitrate load reduction at the basin outlet. And he found that as you increase the amount of wetland area in each one of these subbasins, depending upon how these factors are parameterized in your model, how those factors can affect the output of the model quite a bit. So if you have 1% of restored wetlands in the basin, you can have a range from about 3% down to about 50% of nitrate reduction in the outlet. So these factors are really important, and the reason I kind of circled them is they all go back to that same point. The wetlands need to see the nitrate in order to actually do anything to the nitrate. More recently, we've had Becky Forgrave, who's now a postdoc with the University of Minnesota LTR, and she's been looking at the signal to noise in the Raccoon River watershed in Iowa, and using a similar SWAT model. We do a lot of work in the SWAT world, and is asking to what extent does optimized wetland restoration in headwater basins propagate downstream. And this basin is one I want to focus on first, is number 1 up here. And we've got 10 different scenarios. I just wanted to bookend these 2 to show kind of the highlight of where we are right now. When you restore 0.5% of the wetland area, and you keep the similar 25-to-1 ratio, so for every 25 hectares of land out there, it drains to 1 hectare of wetland. If you keep that ratio in that basin, you'd have a 12%, 12.5% of the basin would be treated, and you'd have a 19% load reduction in that subbasin. Now, if you go up to 4% of the wetland area, which will treat the entirety of the basin, you'd have an 81% reduction in nitrate at the basin outlet, at the subbasin outlet. But the rub is that you wouldn't see much of anything at the subbasin outlet. So what does that look like if you focus all your efforts on that one basin up here, right? And you do 0.5 wetland, or all the way up to 4% wetland, you can get a massive, up to, a pretty massive amount of nitrate removed from that subbasin. But by the time it gets down here to Des Moines, you're not gonna see it because there's so many other things that are going on in that landscape beyond that one basin. So you might get a substantial reduction there, but if you want to see a watershed scale approach, you need to actually look at the watershed and restore wetland on the watershed. So a couple of take homes, and then we'll get into some of the challenges. So non-floodplain wetlands are abundant systems, both within the contiguous US and then across the globe. Non-floodplain wetlands provide critical habitat. Non-floodplain wetlands affect the hydrologic dynamics, both locally and in watershed scales, and they're biogeochemically active areas. But we're finding that in this kind of research journey that we've been on for the past couple of years, that we require, in order for the wetlands to function, they require sufficient storage and processing time. And tiles, for instance, can substantially affect that. And just kind of reiterate, the wetlands need to see the nitrate in order to actually have an effect on the nitrate. So right now we're initially I was going to talk about both non-floodplain wetlands and headwater streams as part of this, but that ended up being a little bit too long of a talk. So I kind of dropped the headwater stuff. We're the team, we're calling them vulnerable waters because both headwater streams and non-floodplain wetlands are lost a lot of their protections of late. And so there are a couple of areas where we're researching the linkage between headwater streams and non-floodplain wetlands, and then trying to explore the connection between those systems and watershed resilience. So how resilient is the watershed to hydrological perturbations or biogeochemical perturbations? And so in this paper that we wrote that came out earlier this year, we're hypothesizing that watershed resilience, if this is kind of a graphic of it, is high when you've got low modification of connectivity and high functioning. So when those systems are out there, they're doing their job, so to speak. But as you start to modify the connectivity or the characteristic functioning, you start to affect the resilience of those, how those wetlands and streams can contribute to the resilience of watersheds. So kind of showing that in parts of the country is a challenge that's out there. One of the things, we spent a lot of time working the SWOT model. The SWOT model lumps wetlands. It's not spatially explicit. What does that mean? Well, we lose a lot of the interactions and we lose a lot of the functions with wetlands when you're working in the SWOT model or with any model, with most models, unless they're really highly modified. In this instance, the model that I showed you that graded in the upper Mississippi River Basin, we did not analyze wetlands that are smaller than 1 hectare in size. That was for computational efficiency. But that means that we lost all these wetlands on the landscape and the interactions that they have and the functions that they perform. I have this dashed line here because the Tucci data set, remember they had the 12.5 hectare kind of criteria. So you have to have more than 12.5 hectares of that 500 meter, the 25 hectare pixel needed to be in wetlands in order to be a wetland. But that's a lot of wetlands that are just not incorporated into the models. So that has an impact, right? You guys probably seen this paper before, maybe by McLaughlin and David and others, and that showed that the smaller wetlands are important to regional hydrology, right? So if you have lots of small wetlands, those wetlands have a different effect than probably bigger effect than a single large wetland on the hydrology of the region. And that can affect the resilience of the region, of the watershed to perturbations. So if we don't incorporate these smaller systems and their contributions, we'll miss what they do. So another challenge is another paper by Matt and Esther and Josh Epstein. This came out recently, was looking at connectivity, right? And so they looked at the Osceola, Swisher, Austin Carey, and Big Cypress. And the line here that I thought was most interesting was this kind of solid one with the arrow on it. And that shows the connectivity of the landscape over a water year, over an actual year. And they found that the wetlands were connecting to the landscape, to the streams across the landscape. And those connections were really important. So 3 to 8 times the daily flux in the streams came from the connectivity of those systems. But oftentimes with these small wetlands, we don't incorporate that into our model, into our approaches to using the landscape and understand the landscape and how wetlands are working on the landscape. And then that can have impacts with the nitrogen dynamics too. So this is a paper that Fred Chang and others put out recently. They have a steady state model, which just said, you've got wetlands on the landscape, and based upon the size of the wetland, it removes nitrate at a certain rate. But then using some data that Mukesh Kumar and others have developed from the University of Alabama, they showed how these wetlands were actually dynamic, right? So some of them dry, some of them are wet, some of them dry, and that dynamism had a pretty substantial effect on the nitrate reduction in the models. So this is a kind of a simplistic, but it's not simplistic because it was a pretty intense model, but it's an approach that shows that we need to incorporate more of the dynamism into our modeling aspects. And this is the size. So you can see again that size has an impact as well. So we need to incorporate the smaller wetlands and the wetland dynamism into the future in terms of assessing what these wetlands are doing at the landscape scale. So kind of the challenges that I have out there in general for you guys, we need to incorporate better ways to identify non-floodplain wetlands. So we've got lots of satellites that are out there now, incorporating higher resolution, different radars, C-band and others to identify the parts of the landscape where you've got a lot of tree cover, inundation, saturation, but not inundation. Like, those are some of the challenges that we've all seen with non-floodplain wetlands. Understanding the dynamism of these systems, like Fred Chang and others have shown, it's important for their functioning at the landscape scale. And then incorporating those findings and the findings of Esther and Matt and others into these hydrological biogeochemical models will be really useful kind of moving forward. And so with that, here's a couple of papers that I kind of went through quickly during the talk today, but I just wanted to kind of give you guys an overview at the high level of where we are with our research and where we've kind of gone over the past couple of years. And you're always welcome to connect to any of us with any questions that you might have about those papers or about the talk or wetlands in general. And I think that's going to be it for now.
All right, let's give Dr. Lane a round of applause. All right, we'll start with questions in the room. I'll see if we've got any courageous folks on YouTube. Go ahead, Peter. I know you got your.
No, sorry. So, Chuck, on
Yes.
the model where you're increasing the area of the small wetlands, you see a reduction in nitrate. Are you in that model? You're also including the fact that it's probably agricultural land that is being transformed back into wetland, and so there's less nutrients being put on the landscape?
Yes, and that was in Gray's model. We really get the upper Mississippi Basin and restoring the landscape. Yes, we did incorporate a decreased nitrogen load onto the landscape.
What's the percentage that's a result of just less nitrogen?
Yeah, so I mean, wetlands aren't going to be the solution in the upper Mississippi River Basin, and I don't have that number offhand.
Don't tell Bill Mitch that.
Really,
Bill, sorry.
right? I mean, they're not the solution by themselves. We also need to put less nitrogen on the landscape. And agricultural landscapes are leaky to begin with, and then we end up having tiles a meter or so underneath the ground that just shunt all the water that gets to them into the stream system. You're missing everything. That's why I've got this hypoxia down here and the Chesapeake and all that. So I mean, it's a fair point. I don't remember the number offhand, but we do incorporate that change in our models.
How much of a change do you, this is just off the top of your head, would there be if you were to take the tiles?
A lot. Yeah, I mean, a lot. And I think it's the hydrology, stupid, right? I mean, that's the question that we always challenge with in the Center for Wetlands. If you want to keep the wetlands and their functions, you got to have the wetland hydrology has to be maintained. And so if you want the function of nitrate removal, keep the wetland wet, and keep it dynamic. Then it should be.
Do you worry that sometimes showing a result of 8,000 acres restored equals 1.8% watershed wide load reduction? Like thinking about nutrients or nitrate as a one target, but we're all in here. We know many ecosystem services of wetlands, and so do you worry that the low bang for the buck that you present is not the full story about the wetland benefit on the landscape?
Right.
Yeah.
It's a good question. In the EPA, we had what we call the Ecosystem Services Research Program for about 4 or 5 years, where we were trying to put essentially dollar signs on ecosystem services that we get from different parts of the landscape and wetlands. We're a big component of that. But again, it's hard. I mean, this is stuff that goes back to early days in the Center for Wetlands and Energy, and just trying to quantify the functions that we get from the landscape. And you're right, there is a relatively small, honestly, relatively small bang for the buck. I wanted to go back to that slide because so if I have my numbers right, so 8,000 square kilometers, so like 3 times the size of Alachua County, something like that. Everyone good with their numbers here? It's not that much, and I think Iowa itself has, I think it lost something like 20,000, say 20,000 square kilometers of wetlands in the past. I mean, it seems like a big number, and this would probably go to Bill, Mitch, and Don Hay and others. I mean, it's a big number on one scale, but when we talk about the entirety of the Upper Mississippi Basin, it's not much. But it's expensive because you got to pay, rent to, if you're not going to farm it, it's going to be wetland. You got to pay rent. You got to figure out how the farmers are going to get their value in the landscape.
Have you worked with like the WRP, the Wetland Reserve Program, or NRCS to basically, I mean, they're funded and a lot more now with the Inflation Reduction Act, right? So billions of dollars coming to agricultural easements and wetland reserve properties. So we all assume, you've modeled whatever percent, but like, can you put some dollars on, or at least some more bang for the buck into that motivation?
Right. So this research is actually being funded by the USDA and FCS, and wetlands are part of the conservation practices that we'd like to explore in these different basins. We're looking at the ACPF, agricultural, ACPF, and remember, agricultural something conservation planning framework. It's a tool where the farmers and the soil managers can assess where in the landscape you might want to put conservation practices to kind of reduce sedimentation, nitrogen loading. And so we're trying to use that and see if we can, what does that tell us about the landscape? If you had all the money in the world and you wanted to create a different river signature for the raccoon, because it would be a different world, right? To be honest, I'd love to see some studies where you have agricultural research stations like Archbold or something like that, and you go down there and go, okay, this is a functional landscape. Let's go and fill the wetlands and see what happens. Let's take a small portion of those wetland systems and quantify what happens when you actually modify the landscape and seriously change things. What would be the outcome at the landscape scale? There's so many different parameters that affect the way wetlands can contribute to nitrogen, to water on the landscape. It's kind of complex.
Yeah, so going back to the nitrogen load shifts, how much of that is due to just holding water and redirecting the volume to evaporation versus actual treatment of that water?
Yeah, that would be a good question for Gray. I gotta say. One of the major parameters in the model affecting the maintenance of water is how much water kind of the hydraulic conductivity of the wetlands, just of the giant lumped wetland. And so that is typically the most important parameter with your model. And so I think that would have probably a bigger impact than ET, but that's a good question.
So looking at this one, you focused in on number one and said it had relatively no effect on the discharge down there, less than 1%. Did you start looking at all of those and try to prioritize which basin would have the biggest bang for it?
Yeah, that's the in-prep part. And so Becky's still working on that. So she moved to Minnesota about 3 months ago, and we still are working with her to get that out. But we're trying to figure out what the signal to noise is in each one of the basins and where you might want to focus your efforts.
And then the last slide you had, I'm wondering about the use of the ratio of areas, wetland areas to the existing basin. Given how data rich we are now in the LiDAR data, you're mentioning, I wondered would a volume ratio be better because of the slope in the landscape.
Right. So what percentage of the landscape is being treated, right? So
exactly, like mean annual rainfall event.
Yeah. And that is a good question. So you kind of get at that a little bit through this drainage ratio of 25 to 1. But that's a good point. And I think where we are right now in understanding the importance of non-floodplain wetlands, geographically isolated wetlands on the landscape, especially in light of recent decisions. And how these wetlands can affect the flow in streams and phosphorus removal, sedimentation, denitrification, things of that nature. I think that the time is quite right for a paper that shows, here's what we potentially will lose. And you saw the one that I put up there with Daniel Uden, and the inundation in the Nebraska sandhills, with climate change going from a certain percentage inundated that's probably sufficient for some of the waterfowl to use, et cetera, to zero, right? And so, I mean, that's a predictive model, and who knows how that will play out. But if we don't protect the wetland resources that are out there, then we will simply not have those places for the waterfowl or nitrogen removal, and we'll have to spend a lot more. To the point, I wish I had the numbers offhand, but I believe in Iowa, it's like every April, May or so, they have to, some of the drinking water plants have to be turned on to remove the excess nitrate from the drinking water supply. So that's not
The
cheap.
true cost.
Yeah, it's expensive. So,
And you've got the carbon and you've got the wildlife habitat, you've got all the other, use and non-use values, so.
yes, yes, and the carbon data is going to be important to have out there for the wetlands.
All right, students, the last seminar of the semester, been the quietest group ever yet to sit in these chairs. So we're gonna sit here until Nick or AJ or someone saves us. Or Rita. I'll call people. My students whose names I know. Hannah often saves us.
So is anyone working on climate change?
Anyone around the climate?
Because we have a big lumped wetland system, and right now we're saying it gets wet for a certain period of time to a certain degree, but we're also changing a lot of the temperature of the landscape, we're changing the timing of the precipitation. And want to kind of venture where, say, 2050, 2100, where we might be with respect to what wetlands can do in terms of ecosystem functions for the globe. Jonas, Florida, Alachua, Gainesville.
More important, less important, more prevalent.
Falling on you guys.
Mhm.
One thing for sure, change.
Yeah.
This is like when I tell my 6-year-old like she has to wear her coat and she doesn't want to wear it. And I have to decide, do I want to push it, right? She wore her coat today. You have no questions for Dr. Lane? Ivana, thank you.
How did you simulate like the extract from nitrogen of the wetlands?
How is the nitrate simulated in SWAT?
Yeah,
Like in the
wetland
wetland.
Right. So Gray Evanston is a great resource. Because SWAT it's a great model, and we've used it for a lot of our efforts here. Gray, again, is really the person who's under the hood in the model. I mentioned during our talk earlier today, when we were at this kind of talking about things around this table here, that in order to do some of the initial modeling that Gray did in the pipe stem, which is 800 square kilometers, he had to more or less go under the hood and do Fortran coding to understand and to make SWAT do what we wanted it to do for the non-floodplain wetlands. And so with the different models, we've kind of dialed back from that because you can't do that when you're talking about the Mississippi River Basin. But I can't answer that exact question. I apologize for that. I'd be back to that.
So are we in the age of like super duper computers, and you work for the federal government of
Right.
the superpower, right? So like why is computational time, and same for you and same, why are we still limited to this computation time? Shouldn't we just have like 1 meter squared models dissolved in 3 dimensions and just it runs on some kind of quantum thing? Like
That'd be great.
what's the holdup?
It's a good question. And there's a paper by Eric and Newman that came out in Landscape Ecology, I think 2-3 years ago, something like that. I mean, they identify 3 of the challenges for landscape ecology. And I think it holds for where we're going, and I want to get them right. I'll try to. Coarse graining is one of them. The middle number problem is the next, and then non-stationary is the third. And I think so. Like coarse graining, you saw where there are thousands and millions of wetlands in the upper Mississippi Basin, but we had to only look at ones that are smaller, or sorry, larger than a hectare. Right, I think a lot of the models were built in earlier time,
Yeah.
and so those models, at least SWOT model anyway, it's still improving, it's still advancing, but I don't know if it is advancing enough to be able to use all the computing.
Yeah, to be like
capacity that we have.
parallelizable and put on GPUs and whatnot, so yeah. I don't know, maybe that's a direction to.
And then, the middle number problem will be looking at each one of those wetlands has its own kind of factors that control the hydrology level, moving the water in and out, nitrate up and down, ET, the percolation rate. But we're lumping it all together into this big one wetland per basin thing, and so we lose a lot of that. Do we have the capability, the technological capability to actually quantify those connections, that how each wetland works and how those wetlands work, vis-a-vis other wetlands in the landscape, precipitation? We should, but you could spend a master's or even a PhD analyzing like a wetland or a small series of wetlands. But then, once you start going out from your small basin and you try and go to the next large basin, even a nested basin, does it scale? I think that's where we're at. And that's why we go to SWOT and we use this big, lumped system. I think, we'll get there. It's not there yet. But the more and more data we have, the more potential we have to use the data.
All right, go ahead.
So you mentioned that there is a computational problem running on these models, especially globally probably, and that there is future steps in using machine learning, but have you thought in using surrogate models to use machine learning on top of those numerical models to speed up the computation?
Great, it's a good idea. I think all right, so there are we haven't tried to explore how we can use machine learning to kind of feed data into the SWOT model. That's one area we've been kind of exploring. I think it's a little bit different than what you're asking about. And I know that one of the another area we've been trying to get more data for. Well, when we talk about, we've been focusing on nitrate for the past couple of years, and so with nitrate data, it's fairly sparse, and so when you end up trying to do, this is a blanket statement, but when you end up trying to do machine learning approaches, you need a lot of data. And so, do we have enough data? You start over from the time. Do we have enough data to actually do those analyses? Not yet, but I think there is potential for using machine learning to get towards those kinds of responses.
So there has to create a synthetic data set from this person.
That
To fill the gaps, like
right.
include
And I think there's the name of the person. There's somebody who's analyzing, using machine learning to analyze like essentially daily nitrate loads in either the raccoon or one of the basins in Iowa, for instance. So we could use those data to kind of incorporate like what they would be able to tell us. Here's the expected nitrate in each one of these reaches based upon this machine learning approach. That would be great to use.
All right, well, let's give Dr. Lane another round of applause.
Any point in time.
All right, thank you everyone on YouTube and online. We will see you next semester for another wild and crazy water, wetlands, and watersheds seminar series. Happy holidays. See y'all later.